We're going to look at two examples of the Gram-Schmidt orthogonalization process. The first example is a problem from your book. This is number 1, part B. It says let A be this 2 by 2 matrix. Use the Gram-Schmidt orthogonalization process to find an orthonormal basis for the range of A. Okay, so to start off, we have to remember what the range of A is. The range of A is all the vectors AX such that X belongs to R2 because this is a 2 by 2 matrix, and this also belongs to R2, and the range is the column space of A. All right, so maybe if we just figure out what the column space of A is, that will give us the range a lot quicker than actually dealing with this formula here, the set notation. So let's find the column space. Remember that to find the column space of a matrix, this matrix is 2, 1, 5, 10. We need to put this into reduced row echelon form. Okay. All right, let's get rid of this 2 here. I'm going to multiply the bottom row by a -2. Remember, you can do it however you want, as long as you get it into reduced row echelon form. So I get 0, -15, 1, 10. I'm going to switch these 2 rows. Let me write out what I'm doing just so I don't confuse anybody. So I took -2 row 2, I added it to row 1, and now I'm going to switch row 1 and row 2. Then I'm going to divide row 2 by -15. And then I'm going to multiply row 2 by a -10 and add it to row 1. And I get the 2 by 2 identity matrix. Okay, remember that the columns that contain the pivots correspond to the vectors that are columns in the original matrix that form a basis for our column space. So this is column 1 and column 2. So in our original matrix, which is right here, column 1, column 2, they form a basis for the range of our matrix. So the range, which is also the column space, is equal to the span of the columns 2, 1 and 5, 10. Okay, also notice that these columns belong to R2. There's 2 of them. We know they're linearly independent because, as you can see, this is our, when we put it in reduced row echelon form, we had these 2 pivots, so they are linearly independent. Look, I can't multiply. If I multiply this one by a scalar, I won't ever, so like if I multiply this by 5 over 2, I won't get 10. So they're linearly independent, and so they span R2. So this space is actually just R2. Great. What can I do with this? Well, I want to form an orthonormal basis, but I want to use the column space, and I actually want to use these 2 vectors. So I'm going to label them V1 and V2 like we did in the description of the Gram-Schmidt orthogonalization process. So we're going to let V1 be 2, 1, and V2 be 510. And our basis is V1, V2. And we want to find another basis, U1 and U2, that's an orthonormal basis. Recall that the first one is really easy to figure out. U1 is just 1 over the length of V1, excuse me, times V1. And by the way, if I do not tell you what the inner product is on the space, if I don't give you a definition of it, or the book doesn't give you a definition, then you assume that the inner product is the standard inner product. So since we're dealing with the vector space R2, the inner product is X transpose Y, which is the dot product of two column vectors. Just keep that in mind. And the reason I bring that up is because the first thing I need to do is figure out the length of V1. So the length of V1 is the square root of the inner product of V1 with itself. So the inner product of V1, 2, 1 with itself, this is 2 times 2, which is 4, plus 1, so 2 squared plus 1 squared is 5. So the length of V1 is root 5. So then U1 is 1 over root 5 times the vector 2, 1. So that is our first vector. Okay, let's find the second vector. Oops. What is U2? Remember, you have a set of formulas to figure out UK for any k greater than or equal to 2 that we gave in the last video. So let's write out what U2 is. U2 is 1 over the length of Z1 times Z1, where Z1 is equal to V2 subtract the inner product of U1 with V2 times U1. So we need to figure out what this inner product is. The inner product of U1 with V2, well, that's the inner product of 1 over the square root of 5, 2, 1, comma, well, V2 is the vector. If we go back up here, you can see that we labeled it as 5, 10. So let's write that. And remember, a scalar can come outside. And this is equal to 1 over the square root of 5 times the dot product of 2, 1 with 5, 10, which is 1 over the square root of 5, 2 times 5 plus 1 times 10, and that is 20 over square root 5. I'm not going to rationalize this, I'm going to leave it just like that. So this number, this 20 square root 5, 20 over square root 5, goes right here. So let's plug that in. Z1 is V2 minus 20 over the square root of 5 times U1. Well, V2 is 5, 10 minus 20 square root 5 times u1 we said is 1 over the square root of 5, 2, 1. This should always happen, by the way. You should be able to get rid of this square root. So we can cancel this out and just make it 5. So we're left with 510 minus 20 over 5, 2, 1, which is 510 minus 4 times 2, 1, which is 510 minus 8, 4, which is negative 3, 6. So this is Z1. Z1 is negative 3, 6. And we're looking for U2, which is 1 over the length of Z1 times Z1. So we need to figure out the length of Z1. The length of Z1, recall, it is the square root of negative 3 squared plus 6 squared, which is 9 plus 36, square root of that, which is the square root of 45. All of this tells me that U2 is 1 over the square root of 45 times negative 3, 6, because that's what Z1 is. And we can simplify this radical. Remember that 45 is 9 times 5, so square root of this is 3 root 5. So U2 is 1 over 3 root 5, negative 3, 6. And I can send this 1 over 3 into everything. I'm going to leave the root 5 out. So I get U2 is 1 over root 5 times negative 1, 2. So let me circle that. And let's put it in red. So we found our two vectors. So our basis, our basis, B hat, which is U1 comma U2, is equal to 1 over root 5. I think the first one was a negative 1, 2. Let me just, if you don't mind, I'm just going to move up so I can recall what it was. Yeah, 1 over root 5, 2, 1. Okay, move back down, sorry. And then U2 is 1 over root 5, negative 1, 2. And if you want, you can send this in. You can say that this is equal to 2 over root 5, 1 over root 5, comma, negative 1 over root 5, 2 over root 5. Now if you want to be extra careful to make sure you didn't make any mistakes, you can take the inner product of these two. You should get 0. Let's just look at it. If we take the dot product of these two, we could pull the constants out and then we get 1 over root 5 times 1 over root 5, which is 1 over 5. And the dot product is 2 times negative 1, which is negative 2, plus 2, that will give me 0. So the inner product of U1 and U2 is 0. And then just take the length of this thing. If you take the inner product of U1 with itself, 2 squared is 4, plus 1 is 5, and then you square this, so you get 5 over 5, which is 1, and the same thing happens here. You get a negative 1 squared is 1, 2 squared is 4, add them together, 5, and then you get double of these. So this is an orthonormal basis.